Control valves 1. Ideal characteristics. Introduction. The control action in any control loop system is executed by the final control element. The most common type of final control element used in chemical and other process control is the control valve. A control valve is normally driven by a diaphragm type pneumatic actuator that throttles the flow of the manipulating variable for obtaining the desired control action. A control valve essentially consists of a plug and a stem. The stem can be raised or lowered by air pressure, and the plug changes the effective area of an orifice in the flow path. Figure 1 shows a control valve. It is a pneumatically operated control valve. A typical control valve action can be explained using figure 1. When the air pressure increases, the downward force of the diaphragm moves the stem downward against the spring. Request. It is hoped that this lecture is going to be useful to you. Please press like. Please. Classifications of control valves. Control valves are available in different types and shapes. They can be classified in different ways based on A. Action, B. Number of plugs, and C. Flow characteristics. Figure 2 shows air to open and air to close valves. Action. Control valves operated through pneumatic actuators can be either air to open or air to close. The schematic arrangements of these two actions are shown in figure 2. Valve A are air to close type, indicating if the air fails, the valve will be fully open. Opposite is the case for valve B. They are designed such that if the air supply fails, the control valve will be either fully open or fully closed, depending upon the safety requirement of the process. For example, if the valve is used to control steam or fuel flow, the valve should be shut off completely in case of air failure. On the other hand, if the valve is handling cooling water to a reactor, the flow should be maximum in case of emergency. Figure 3. Single-seated and double-seated valves. B. Number of plugs. Control valves can also be characterized in terms of the number of plugs present, as a single-seated valve and double-seated valve. The difference in construction between a single-seated and double-seated valve are illustrated in figure 3. Referring figure 1, only one plug is present in the control valve, so it is single-seated valve. The advantage of this type of valve is that it can be fully closed and flow variation from 0 to 100% can be achieved. But looking at its construction, due to the pressure drop across the orifice, a large upward force is present in the orifice area, and as a result, the force required to move the valve against this upward thrust is also large. This type of valve is more suitable for small flow rates. On the other hand, there are two plugs in a double-seated valve. Flow moves upward in one orifice area and downward in other orifice area. The resultant upward or downward thrust is almost zero. As a result, the force required to move a double-seated valve is comparatively much less. But the double-seated valve suffers from one disadvantage. The flow cannot be shut off completely because of the differential temperature expansion of the stem and the valve seat. If one plug is tightly closed, there is usually a small gap between the other plug and its seat. Thus, single-seated valves are recommended for when the valves are required to be shut off completely. But there are many processes where the valve used is not expected to operate near shut-off position. For this condition, double-seated valves are recommended. Ideal characteristics. The control valves acts like an orifice, and the position of the plug decides the area of opening of the orifice. Recall that the flow rate through an orifice can be expressed in terms of upstream and downstream static pressure heads as shown in equation 1, where Q equal to flow rate in meter cube per second, K1 equal to flow coefficient, small a equal to area of the control valve opening in meter square, H1 equal to upstream static head of the fluid in meters, H2 equal to downstream static head of the fluid in meters. G is equal to acceleration due to gravity in meter per second square. Ideal characteristics. Now the area of the control valve opening A is again dependent on the stem position or the lift. So if the upstream and downstream static pressure heads are somehow maintained constant, then the flow rate is a function of the lift Z, that is Q equal to function of small z, equation 2. The shape of the plug decides how the flow rate changes with the stem movement or lift, and the characteristics of the Q versus Z is known as the inherent characteristics of the valve. Let us define M equal to Q upon Q max and X equal to Z upon Z max, where Q max is the maximum flow rate when the valve is fully open and Z max is the corresponding maximum lift. So equation 2 can be written in terms of M and X as M equal to function of X, and the valve density is defined as the dm by dx, or the slope of the curve M versus X. In this way, the control valves can be classified in terms of their M versus X characteristics, and three types of control valves are normally in use. They are type A, quick opening; type B, linear; type C, equal percentage. The characteristics of these control valves are shown in figure 4. It has to be kept in mind that all the characteristics are to be determined after maintaining constant pressure difference across the valve as shown in figure 4. This is figure 4, and we can see here that delta P is the pressure across the control valve and delta P is constant, and the flow characteristics are like this. This is the quick opening characteristic, this is the linear characteristic, and this is the equal percentage. Different flow characteristics can be obtained by properly shaping the plugs. Typical shapes of the three types of valves are shown in figure 5. This is the typical shape for equal percentage valve. This is the plug shape for linear control valve, and this is the plug shape for quick opening control valve. For a linear valve, dm by dx is equal to 1 as evident from figure 5, and the flow characteristics is linear throughout the operating range. On the other hand, for an equal percentage valve, the flow characteristic is mathematically expressed as dm by dx equal to beta times m, equation 4, where beta is constant. The above expression indicates that the slope of the flow characteristic is proportional to the present flow rate, justifying the term equal percentage. This flow characteristic is linear on a semi-log graph paper. The minimum flow rate M0, flow rate at x equal to 0, is never 0 for an equal percentage valve, and M can be expressed as M equal to M0 exponential raised to power beta x, equation 5. Rangeability. Rangeability of a control valve is defined as the ratio of the maximum controllable flow and the minimum controllable flow. Thus, rangeability equal to maximum controllable flow divided by minimum controllable flow. Rangeability of a control valve is normally in between 20 and 70. The next lecture is named Control Valves 2. In this lecture, effective characteristics of the control valves shall be discussed. Request: it is hoped that this lecture is useful to you. Please press like. Please subscribe.